All right, I think we're all set to go. Um, cool. So welcome back, everybody. All right. Procedural stuff. So first of all, I'm going to end the class 20 minutes early today. So we're going to end at 2:50 instead of 3:10. Um, reason being, I have a parent-teacher conference scheduled at 3:10, so I need time to get to the school and stuff. So on the other hand, Monday is a holiday, and so the Monday section of this class will not meet on Monday, and so we kind of get an extra 2 hours next week against the other section. So we're going to, be able to go over some other stuff that we might not get to in the A section. So some optional material. But cutting 20 minutes off today's class will easily make that up on Tuesday, so it won't be a problem as far as coverage of essential material. But we have, a little bit of extra breathing room today and next week because of that 2 hours we lose in the morning class on Monday. So I'm planning. Sorry, say again.
Is it going to be a Freaky Friday story?
Oh, I don't know. That would be fun. I don't think I have a Freaky Friday for this class, unfortunately. But who knows? Maybe. um, but I am planning to continue talking about trees, digging deeper into tree algorithms, starting with the significance of height, thinking about what the height of a tree actually relates to and why we're interested in it. Moving up to talking about balance, and then I definitely want to get through deletion of data from trees today, and that's sort of the last piece of PA4 that we haven't really gone over yet. And yeah, we're going to start with height and review that from Tuesday because that was like at the end of class. So those are my essential plans, and we'll talk more about PA4 strategies along the way and so on. So any questions you want to go over before we start on all of that?
I guess I have a height question, but I'll wait till we get to that.
Oh, you can ask it now.
Okay,
Yeah.
I was just gonna say, I would imagine height. The reason why we're so interested is to make sure that, because the farther you have to travel down, right, the longer it takes you to get through your algorithm.
Exactly.
And whatnot.
Yep.
So you want to make sure it's balanced so that you're not, or so that it's kind of more order. What is it? Order n or
Actually,
log n.
log in. Yeah, exactly.
Yeah. So that way it's not okay.
Yeah, it's all about performance. Yeah, so we'll spec that out in a lot of detail.
Well, that doesn't tell the whole story, though, right?
Height does not tell the whole story, but it's a pretty good first level metric.
And is there a way to curb the height so that you have, I guess, a more shallow tree?
Yes, and that's what we'll be doing in about another week or two when we talk about AVL trees and balancing trees. We'll be trying to minimize the height relative to how much stuff we have in the tree.
Okay. And I'm assuming there's some kind of a limit to that, right? Because you can only do so much.
Exactly.
Structure, I would imagine. Okay.
Yeah, there's only so much stuff you can put in a tree of a certain height, and beyond that, you've got to make the tree taller, right? You got to have nodes at a deeper level. But what we're really trying to do is avoid pathologies where, say, you have 7 pieces of data and your tree looks like that, and it's got this very tall height to it when in fact it could have been done like this with a much shallower tree.
Gotcha. So would you say with more data, the hash table's just the best way to go, kind of?
No, trees are really going to be good.
Okay.
It's very doable to keep a tree balanced, to keep that height pretty low. And as we'll see, if you have 1 trillion pieces of data that you store in a binary tree and the tree is balanced, the height's approximately 40. And 40 operations, no problem. I mean, you can do that in a few milliseconds, worst case. So this is going to be a really, really efficient way to store even a large amount of information.
So if you're looking at a height of 40, then you're looking at 40 operations total,
Yep.
like in worst case scenario kind of thing.
Yeah, if you're searching for one thing out of a trillion, it takes 40 comparisons.
Okay, and that's a matter of milliseconds, basically.
Yeah, I mean 40 is not something we worry about. A trillion is something we worry about. And
Very
this,
close to the high-low.
yeah, this is exactly high-low. If you say think of a number between 1 and a trillion, you can guess that number in 40 guesses, right? If you know the algorithm and you apply it correctly. And that's pretty fantastic. I mean, 40 guesses to pick a number between 1 and a trillion, that's pretty impressive.
Yeah.
And another thing you can get from this, and we'll play around with this in CSE223 maybe, is this game of 20 questions. And you may have played this. You get to ask yes/no questions and try to guess what somebody's thinking of. And so it's like, is it an animal? Is it furry? Does it live in North America? And with just 20 questions, you can do a pretty good job of figuring out what somebody is thinking of. And it's because we can take all the things that somebody might be thinking of and put them in what's called a decision tree. And 20 questions corresponds to the height. And a tree with a height of 20, that's roughly 1 million nodes. So you can differentiate between 1 million different possible things with just 20 questions. Let's see, when they say a pyramid scheme can only go through like 5 levels before it... Yeah, exactly. Yeah, so this kind of doubling of the amount of stuff each time you add one more level to the height, that's where we really kind of, get into these big numbers, millions, billions, trillions, without having to do a ridiculous amount of work.
I know we're not there yet in terms of the material in the CSE course, but I have to think it's really clever if you can pull off height with a static or some sort of global or a member variable.
Okay. You mean calculating height?
Yeah.
Yeah. Cool.
Like, something I've noticed we haven't really done with any of our data structures so far is we don't have like a storage of state per se. Like, we could only really make one hash table because we have a global for size, but if we wanted to make more, they each would have to have their own state for how big their hash tables are, right?
Right.
Wouldn't we want to do something like this for this tree structure so we could have like, okay, so what's its height? Is it balanced? Is it, I guess, or some other information on the state of the structure? Wouldn't we want to have that in some way or another?
So what you're describing is what we're going to call objects in 223 when we get to Java. We have simple variables in C, integers, characters, and so on. We have structures in C that let us take, a couple of integers and a character array and a double and glom those all together into one thing called, a supernode or whatever, right? An object will take that further and will also glom code into that structure. So we'll have a single thing that will have code and will have variables and can also have things like, static integers, flags, state variables, all contained within this one object. And so we could create, a hash table class and create an object of type hash table. And each hash table we create would have effectively, its own data, its own variables, its own hash size global, and its own code for manipulating that set of data. And that's really the right way to do, the kinds of things we're doing right now in some of these assignments where we're kind of cheating and using a global, because each thing of type, hash table would have a global hash size, and it would be different from the hash size stored in another thing of type hash table. So we're going to get to that in Java, and it's probably going to feel really right by the time we get there, because we've been doing it, and kind of faking it in C so far. But for trees in particular, we're actually not going to need that. If we want to figure out the height of a tree, we're just going to calculate it. Because it's going to be so easy to do that calculation, and it's going to be so fast to do that calculation, relatively fast.
I'm curious. I couldn't quite figure it out with my intuition. I was really thinking about it yesterday.
Yeah, it's an interesting challenge to try to calculate the height. So let's review what we mean by height. Here's a tree. I'm gonna have to close the shades, I know, because we're getting that Alfred Hitchcock kind of creepy shadow thing going here. But here's a tree, and height comes from depth, and the depth of a node is basically the number of steps from the root to that node. So if you start at the root, take 1, 2, 3 steps, that gets you down here. Or 1, 2, 3 steps gets you over here. So all of these things, if you draw it neatly, have a depth of 3. All of these things have a depth of 2 and 1. And the root always has a depth of 0 because the amount of steps from the root to the root is 0. You don't have to go anywhere. All right, so then the height of the tree is just the depth of the deepest node. So it's the maximum number of steps from the root to any node in the tree. And in this case, either one of these would define the height to be 1, 2, 3 or 1, 2, 3. So if you wanted to do this with a loop, right, you basically have to start at the root. And every time that you move to a child, increment some kind of global variable to say, okay, now I'm at a depth of 1, now I'm at a depth of 2. And every time you hit a leaf node, or every time you change a depth, see if it's bigger than another global variable that's recording the maximum depth. And if the depth gets bigger than, whatever your maximum is up to that point, you've got a new maximum. And when you finish that whole process of visiting every node, traversing the tree, you'll have saved, what the maximum depth is. That's the height of the tree. But that's a lot of work, right? That takes a lot of housekeeping, and you're going to need to implement a stack to keep track of, where you are in the process of traversing the tree. But there's a completely different way to define the height, and this is using recursion. And it's based on the following observation, that if I just think of some node and I look at its depth, the depth is, 1, 2, 3, the number of steps from the root to that node. Now, if this tree itself is a left subtree of a bigger tree, I immediately know what the depth of this node is in this bigger tree. Right? If this node is 3 steps from this root, 1, 2, 3, and this is now the left child of the root of a bigger tree, the depth of this node in that bigger tree will just be 1 more. It'll be 4. From the root, I go 1, and then I do my usual 3 steps, 2, 3, 4. My depth will be 4. So this is the first observation. If I just think of this right subtree, and I calculate the depth of every node, I get exactly 1 less than the depth of that node in this original tree. Does everybody see that?
So I got a quick question, because
Yeah.
we went through our height function and kind of a good way to do it the other day, and I have it working, and it is giving me the same as your sample executable.
Okay.
But I'm curious, because we're calling on it recursively, I understand how that works, but because we're declaring a variable of integer type, is it just doing a tally in the background, and just every time it calls that function, it's keeping note of that, or how does that actually increment?
It's an interesting question, because when we write the recursive function, all we ever do is add 1 to something. But if the height of the tree is 9, that height function will basically get called recursively 9 times in such a way that each time it returns another higher integer, and when we add 1 to that, we count up one more level. And after we do 9 returns, we'll have added 9 to an initial height of -1 for a null tree, and that'll bring us up to the actual tree height. But it's really kind of weird to think about like where that calculation is actually happening, and it's part of the magic feeling of recursion. It's like it happens in the ether or something. But for
It's just funny, like, you know, because obviously we're used to the I++, or,
Mhm.
you know, incrementing it ourselves in some way, and I guess you're not really doing that. Well, I guess we're doing. No, yeah, I guess we're not really doing that here, and we're just kind of saying, you know, do this for us and give us a number back.
yeah, yeah. It's fun and illuminating to take a relatively small tree, maybe 7 nodes, and try to actually run through what the computer goes through in executing your height function. And you can do that, every time that you make a new call to your function, get a new sheet of paper and start, running your algorithm on the argument that's passed to that instance of the height function. And when you return, go back to the previous sheet of paper with your previous variables, and you can go through the recursion by hand like this. And in the process of doing that, you kind of sometimes begin to see sort of how you're actually traversing the tree and where that addition of say the height is coming from. And it's interesting.
Yeah, no, it just seems it's kind of a, at least it's kind of a weird concept.
Yeah.
I get, what it's doing and why it's doing it, but the incrementing part was kind of weird to me.
Yeah, yeah. And then eventually,
To me too.
say again?
That's what's weird to me too. Like I finished the search function, and when I actually got it working, it felt like pure magic.
Mm-hmm. Yep.
Where as soon as I get that correct one, I return 1, and if I return 1, I just return 1 again and again and again. I walk all the way back up the tree. But
Yep.
The thing that confuses me here is, how do I walk all the way back up the tree with the correct height?
Because when you get all the way down here and you try to find the height of this child, which is -1, your function just returns immediately. It says if the tree's null, return -1. And your call to the height function on this node says add 1 to the value I got back. That returns a 0. And the call to this tree, when you called height on this one, it returns a 0. The code says add 1 to the height of the subchild. So this returns 1, and this will return 2, and this will return 3. And it's really kind of freaky.
How exactly do you know specifically it's 3 and not say 2 there, like on the left half of the tree? You get something all the way down to the bottom there, and it ends up being 2, but it's not 3, which is the actual height.
Because the first call to the height function is going to do 2 things. It's going to calculate the height of the left subtree, which will be 2. Will be 1. It's going to calculate the height of the right subtree, which will be 2. It's going to say take the larger of those and add 1. And the larger of those is 2, so it'll add 1 to 2 is 3, and that's what it'll return.
Okay.
Now, out of curiosity, because I've got a search function and it works great, but I didn't do anything recursively in there.
Mm-hmm.
That's pretty normal.
Yeah, but you definitely want to do a recursive search for the assignment.
Okay.
The one of the goals of the assignment is to flex our recursion muscles and get comfortable with those.
Okay.
So if you got an iterative search working, that's awesome, and maybe rename that function to iSearch or something, and then try to implement the recursive one. All right, so let's develop the height function, which is based on this observation that the depth of a node in a subtree is 1 less than the depth of the node in the original tree. And since the height of a tree is the depth of the deepest node, the height of this tree will be the depth of the deepest node, Well, if the largest subtree in the original tree is this one, the depth of the deepest node here is 1 less than the depth of the deepest node in this original tree. In other words, the height of this tree is 1 less than the height of the original tree. But it could be that, you know, the tree on the left has a much deeper node, in which case the depth of this subtree would be 1 less than the depth of the original tree. And so we don't know which one of these is the deepest, but whichever one is, whichever subtree has the greatest height, that height is 1 less than the height of the original tree. And so that's the motivation for this recursive height function. So we can say height of t, and it's going to return an int. And if t is null, that's an empty tree, its height is -1. Otherwise, we say left equals the height of the left subtree, and this is a safe call now. As long as t is not null, it's a node, it has a left child. This left child could be null, that's okay. We can call height with a null argument. The only segfault danger is if we try to dereference null. So if t is null, t arrow left will segfault. But we're ensuring that t is not null by checking that in the very beginning. So we're safe to say left equals height of tree arrow left, and right equals height of t arrow right. And then just return 1 plus whichever is the largest, left or right. And so that's a way to calculate height, and we don't have to keep track of anything. We don't need a global variable to record how deep we've gone. We're simply using this different way of looking at height. Yeah, go ahead.
Man, that is so cool. I get it now.
Okay, awesome. All right, so why does height matter? Right? Why are we interested in this other than, you know, it's something else to calculate? And as someone said in the beginning, it relates to performance. Right? So here we've got 7 nodes stored in a tree, and this is a binary search tree. But if we're looking for something that's not in here, it could potentially take us 1, 2, 3, 4, 5, 6, 7 comparisons to conclude that the thing we're looking for is not in our tree. But here's the same 7 pieces of data arranged in a different tree, and if we're looking for something that's not in this tree, it's going to take us at most 1, 2, 3 comparisons to conclude it's not in the tree. And if we're looking for something not in the tree, how do we know it's not in the tree? Because we get to a node that has no child in the direction we want to go. In other words, we get to a leaf node, or a node that, you know, is missing 1 child. And since the height of this tree is 2, the depth of the deepest node is 2. And whatever the depth of a node is, that's basically how many operations, how many steps you have to take to get there. So this node has a depth of 2 because you have to do 1, 2 links to get there, which means if we're comparing at each point, we're going to have to do 1, 2, 3 comparisons. So 3, 2, you know, plus or minus 1. But the number of operations we have to do to search for something, or to add something, or eventually delete something, is basically the order of the height. And this is a really good performance characteristic. So if you think about what you can store in a tree, so here's a null tree. Its height is -1, and it has 0 nodes stored in it. Here's a single noded tree, right? It just has a root. Its height is 0, and it has a single node. Here's a thing with 3 nodes, and its height is 1. Here's a thing with 7 nodes, and its height is 2. So what's the order of growth here? How are these numbers growing? Each time we increase the height by 1, what's happening to the number of nodes? Is there a pattern here?
Felix, it's that one thing that we were talking about yesterday. I can't remember the name of it.
Mm-hmm. Like a recurrence relation?
Yeah.
Yeah. So if we don't see a pattern in these numbers, sometimes when you look for a pattern in something, look a little bit to the side. Right? This is something animals do when they're hunting. If you're looking for a pattern, don't look directly at the thing you're trying to find a pattern in. Look at something nearby. And in this case, if I were to add 1 to each of these numbers, I suddenly start to see something that may look like a pattern. And yeah, people are putting this in chat now. It's powers of 2. And sure enough, if I set my height equal to 3, and I draw this, the next tree will have 15 nodes in it, which is 1 less than the next power of 2. So this could be something like, 2 to the height plus 1 minus 1. So if height's 3, 2 to the 4th is 16 minus 1 is 15. But it's on the order of 2 to the height. And this makes some sense if we think about what happens if we wanted to add another layer to this tree. So here's the tree of height 2. If we want to make this a tree of height 3, how much more stuff can we add to this? Well, every node in this tree has 2 children except these deepest nodes, which are all leaf nodes and have no children. And since every node can have 2 children, we can add 2 nodes at the bottom here. 2 nodes for each node. Which means if you look at the number of things at each depth, at this depth we have 1, here we have 2, here we have 4, here we have 8. If we were to add another layer, that layer would have 16 children. Because each of these 8 leaf nodes can have 2 children. So each time we add 1 to the height of the tree, we can add twice as many nodes as we had in the deepest layer previously. And that's really where this order 2 to the height is coming from. This is why we're roughly doubling the number of nodes each time. If we add another layer, we're going to add 8 more, and we're going to add 16 more, and this is 15 nodes. So we've got 15, we're going to add another 16. That's going to leave us with 31, and if we add another layer at the bottom, we're going to add 32 new nodes, and that's going to double us roughly to 63. And this is why trees are so efficient for storing information, because how many times do we have to double before we get to a trillion? Well, it's about 40 times. And so a tree with 40 levels on it is going to have a trillion things in it. Which means, if someone asks you on a test to draw a picture of a tree with a height of 40, don't do it. Because you're going to have to draw a trillion circles, right? It's a trick question. So it's bad for artists, but it's really good for storing information. And, we can store a trillion things in a linked list, but to search for something in that list, we're going to have to potentially check a trillion things. Say again?
Did I cut out?
Yeah, I cut out. Yeah.
Well, that's weird. I cut out at this point yesterday. Okay, can you hear me right now?
This class is so cool.
Can you hear me? Okay, hold on. Let me check my audio. Da 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 da. Oh, and there goes my network. All right, am I back?
You're back.
Whoa, okay. That's weird. I think this happened yesterday about the same point, but my network just went out. Maybe they are watching, you know.
Do you have CenturyLink? Because I have that issue.
No, I've got cable. Maybe this is the moment when I disclose some information about recursion that somebody uses in the future to build a time machine, and it does bad things, and you know.
They showed back up to cut your cable.
Exactly, yeah. Because they never just like do the direct route. It's always like, oh, let's go, you know, tell a children's story to his great grandfather so he doesn't get married. All right. Well, I'm going to post the YouTube recording anyway, so the future will be preserved. All right. So I don't know where I cut out, but basically I was saying, you know, each time that we add another layer, we double the amount of stuff in the tree. And so this is why if you want to store 1 trillion things in a tree, it only takes 40 or 41 levels of data to get all of that in there. And so that's useful because it's a performance factor, right? If you had 1 trillion things in a linked list, just laid out side by side, and you wanted to search that list for something, potentially you have to do 1 trillion comparisons. That's 10 to the 12th, right? Trillion comparisons to search for something. If you put the same data in a tree, it's 40 comparisons, right? Which is a lot faster than 1 trillion. So that's why height is critical. Go ahead.
What about if there's more than just 2 connections?
More than 2 children per node?
Yeah.
Well, things get even better. So if you had, say, 3 children, right, and so on, then the amount of stuff in the tree is roughly 3 to the n. And so it's you know, better, but it's better by some, I don't know if it's a constant factor. It's not. But it's not as much better as you might think. It's really the idea of, you know, bifurcating or trifurcating at each level that gets us this big hit. And we can improve, you know, the performance by having 3 children or having 26 children and so on. But seriously, if we've got 1 trillion pieces of data and it only takes 40 operations, if we can cut that down to 20, it's probably not a big deal in you know, some cases. Now, if you're going to search data, you know, and you want to search 1 million times a second because you're Google, those kinds of small time savings can be significant. But if we're, you know, writing a license plate program for 1 trillion license plates, and it only takes us 40 iterations to find a plate, that's probably plenty fast. And splay trees and tries. So this is all good in theory, but there's still, you know, the reality that sometimes you build a tree and it comes out looking like this, right? It can be all kind of lopsided. And instead of, you know, getting 7 things in a height of 2, we need a height of 6 to get that. And, you know, worst case, 1 trillion pieces of data in a tree, if your tree looked like this, it would have a height of 1 trillion. And that's horrible performance, right? So the idea of a balanced tree is one that looks more like this than like that. And we can think about balance kind of intuitively as the idea that when we're filling in data in the shape of a tree, we try to sort of fill in the upper levels before we go down to deeper levels. So if you were to draw a tree, you would, you know, once I've got a node at this level, I'd want to put another node here before I come down to this level. And if I'm filling in nodes at this level, I'd want to put in a bunch of nodes at that level before I came down to a deeper level. And so it's trying to fill things in from top to bottom before we get too deep, right? Keep things nice and fluffy and evenly balanced. And similarly, you know, we don't want to see things like this. I mean, this looks balanced in some sense. We've got the same amount of stuff on one side as the other. But it still misses this idea of taking advantage of each layer before we move to a deeper one. Because we've got a lot of unused nodes throughout this whole tree. Right? There's a bunch of nodes in here that we could have filled in that we just have sitting as null. And meanwhile, we've come way down here to these deep levels down here at these leaf nodes. So this will end up being an unbalanced tree. And unbalanced means we're not getting this nice 2 to the n increase in the amount of data each time we increase the level. This has got a height of 6. We should have probably, you know, 100 some nodes in here. And yeah, balancing is challenging, and we'll talk about that in a few weeks, how to do it. But first we're going to talk about what it means to be balanced or unbalanced and how we can test to see if a tree is balanced or not. The other way to analyze this, right, so this analysis over here is looking at the height of a tree and saying how much data can we store in there. The other way we can do this is to ask the question, what's the height of a tree with n nodes? So here we were looking at, if your height is this, what's the number of nodes? And the number of nodes was roughly 2 to the height. So number of nodes is approximately 2 to the height. So if we know what the number of nodes should be, how do we figure out what the height is? Anybody got an inkling for this? I saw it earlier in chat. The height is roughly the logarithm of the number of nodes. And so if you're rusty on logarithms, if 2 to the 6th is 64, then the logarithm of 64 is 2. If 2 to the 10th is 1024, then 10 is the logarithm of 1024. So the logarithm of a number is the exponent that gets you that number. So the log of 1024 is the thing that if you raise 2 to it, you get 1024. In the terms of trees, the logarithm of the number of nodes is the height of the tree that gets you that many nodes. It's the value of h such that 2 to the h gets you that many nodes. And so the height of a tree is...
It's not going to be that log too, right?
Say again?
But if it's... I think I know where you're going with this. Where if it's not... If you're trying to see if the tree is balanced or not, it's the height of the tree, the maximum height of the tree should tell you the... I got mixed up for a second. The log base 2 of the height should tell you how many nodes there are, but if there aren't that many nodes, then it's unbalanced, right?
Yeah, yeah. Or same thing worded in a slightly different direction. If your height is bigger than the log of the number of nodes, it's probably not balanced. Right? So the height, so what's the minimum height for a tree with n nodes? The log of the number of nodes. What's the maximum height? It's just n, right? Just make a big long single tree with node following node, and it looks like a linked list at an angle, right? So the maximum height is going to be whatever the number of nodes is. But the best case, if we sort of pack it up and make it nice and full and fluffy, the height could be as small as the logarithm of the number of nodes. And so if we have 1 trillion nodes, the log of 1 trillion is roughly 40. And so we could, have a tree with a height of 40. And if the tree is balanced, that's what the height would be. But if it's not balanced, the height will probably be bigger than that, and it might take 41 or 45 operations, or 100 or 1,000,000 or 1 trillion, right? So this ideal gets us that nice performance. And so if you ask what's the order of complexity of searching a binary search tree, that's where we say it's something like order of log n, where n in this case means the number of nodes. One more refresher on logarithms. In computer science, when we say just log, we usually mean log base 2. In other science classes, chemistry, physics, if you just see log, a lot of times it means the log base 10, or what's called the common logarithm. And when you see ln, that's a logarithm-based e. That's called the natural logarithm. That's the one that's sort of the most sort of canonical, right? So what power do we raise e to in order to get a number? E is 2.718, etc. What number do we raise 10 to? Well, that's easy because, 1,000,000 is 10 to the 6th. So the log base 10 of 1,000,000 is 6. You just count the number of digits. But log base 2 is mostly what pops up in computer science because we do so many things that are like trees, or things that we call divide and conquer, where you're taking a problem and splitting it into 2 pieces and then tackling those sub-problems, which is really what a tree is doing. It's taking a search problem and saying, oh, let's just search half of the problem space. So I'll generally stick to log base 2, but a lot of times, especially with like order of complexity, you just see log, you can usually assume it's log base 2. All right, so is a tree balanced? How do we know this? And there's different ways we can define characteristics of a tree that will tell us if a tree is balanced or not. But like most things, we're going to use a recursive definition of balance. So a tree T is balanced if case 1, T is null. So by definition, a tree with no nodes in it, we're going to call that balanced. So empty tree, the root is null, there's no data stored in it, it's balanced, right? I mean, there's no stuff on either side of the root, there's no root, it's pretty hard for it to be unbalanced. So by definition, a null tree is going to be balanced. So it's balanced if T is null, or a tree is balanced if all 3 of these are true. And you have to check all 3 of these. And we'll see cases where some of these are true and the tree is still not balanced. It's got to be all 3 of these things. So 1, the left subtree of T has to be balanced. The right subtree of T also has to be balanced. And the left and right subtrees have to be close to each other in height. And so more precisely, the absolute value of the difference between the height of the left subtree and the height of the right subtree can't be any greater than 1. So those are the 2 ways a tree can be balanced. Either the tree is completely empty, or the left and right subtrees are balanced and the left and right subtrees have heights that are close to each other. If all 3 of these are true, the tree is balanced. If neither of these are true, then the tree is unbalanced. So I'm going to keep this definition nearby, but we're also going to remember a null tree is balanced. That one's not incredibly interesting, but let's remember this 3-step requirement. And let's look at some trees and analyze them and see if they're balanced or not. So there's our 3-step requirement. So we know that a null tree is balanced, because that's the case that I covered up. What about a tree containing a single node, just a tree with a root and nothing else in it? Is that going to be balanced, and why or why not?
I would say yes, because there's only one node in there, and anything to the 0 power is going to be 1, right?
True. Can we back that up with the definition of what it means to be balanced? You are right, it is balanced.
So, well, it's going to be log 2 of 1, right? Because there's one node, which would be 0. Is that correct?
Okay, so you're asking if we've got as much stuff in the tree as we could for that height, and that's true. That is the case, and that is a reason why it's balanced. But let's work with this definition, because sometimes that approach will lead us astray, and we'll see some examples of that.
So if we followed 3, then left and right would both be less than or equal to 1.
Yeah,
Less
so
than 1, obviously.
so what's the left subtree of this thing look like?
Would just be null.
It's null, right? The left subtree is a null tree, and so is the right subtree. So we asked 3 questions. Is the left subtree balanced? Is a null tree balanced? Yes, we just wrote that down. So step 1 is satisfied. Criteria 2, T right should be balanced. Well, T right is null, and a null tree is balanced. So that criteria is satisfied. So the third criteria, the heights of these have to be within 1. So what's the height of a null tree? Do you remember this?
-1.
Height equals -1. And -1 minus -1 is 0. Absolute value of 0 is less than or equal to 1. That is also true, so this is balanced. And that's the same procedure we can use for any tree. So let's keep working this. Let's look at a tree like this. A little tiny lopsided tree. So is this balanced or not?
No.
Okay, why not?
The left is balanced, but the right... Oh, wait. No, I guess the right would be balanced.
Yeah, because the right
Null.
subtree is null. So the left subtree is a single node, which we've decided is balanced. The right subtree is null, which we've decided is balanced. And so what's the height of the left subtree?
It's going to be 1.
So this is an edge case. The height of a single node is actually 0.
Oh, because then you add 1 to it.
Yeah, and the right subtree is null. The height is -1. 0 minus -1 is 1. Absolute value is 1. That's less than or equal to 1. So this is also balanced.
So we don't start getting into unbalanced until you start adding at least 2 nodes to the left side and nothing to the right.
Right, right.
Okay.
And so this, we don't have to do this one, but this is certainly going to be balanced. Right, left subtree is a node, right subtree is a node. Those are both balanced, and the height of the left and right subtrees are 0, which certainly satisfies this condition. So this will be balanced.
So the second example, would that just account for odd number of data, basically? Saying like,
you know, it's okay to have one less node on this side than this
Mm-hmm.
because we might have odd amount of data.
Yeah, and that is another way to look at this, right? If we only have two things in our tree, we can't do better than this. I mean, this node could be over here or it could be here, but there's no way to make it look more balanced, right? Because if we only have two things, one of them's going to be the root, the other's going to be a child. So any tree with only two nodes in it has got to be balanced. I mean, there's no way that we could do anything more balanced than this.
Okay, so that makes way more sense for the third rule there. I was really confused about it for a second.
Okay.
I was also thinking about how, you know, if you're going to have, like say the second tree there, if you're going to have one more node, but not the other four nodes to make it fully complete, would it still be balanced? Now that makes sense.
Okay, cool. All right, so let's try this one. So what do you think about this tree?
It would still be balanced, right?
So the left subtree looks like this, and we've seen that's balanced. And the height of this left subtree is 1. And the right subtree is a single node, and we've seen that's balanced, and the height is 0, and these heights are within 1. So this is still balanced.
So even if you added a node to the right of that left side node, so if it was two child nodes on the left one, that would still be balanced then because the height wouldn't change.
So if I did this,
Yeah.
yep, that's going to be balanced too. And again, we can say, you know, if we wanted 5 nodes, well, our first 3 are sitting like this. This is really, really nicely balanced. The 4th node has got to go, you know, either here, 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 or here. And if we add a 5th node, right, and we put it here, here, or here, that's, you know, as high up in the tree as we could possibly do. And for n nodes, there's always a way to make a balanced tree with n nodes. There's always some shape of the tree that will be balanced. But if we did this, what are we going to find there?
I would say that's still balanced. The
Mhm.
heights are going to be the same.
Yep. This is still balanced because the left subtree looks like this. That's balanced. Right subtree looks like that. It's balanced. Both of them have a height of 1, so the difference in heights is 0. That's still balanced. And even though this looks kind of like, you know, it's sort of lopsided, it's two big long sticks, you know, sitting on each other, it's still balanced. Again, you know, we could put this node here, or here, or here, right? And all of those are going to be as high up in the tree as possible. But now we can look at, you know, something like this.
This would not be balanced at all.
Right. So here's the left subtree, and you know, a thing with well, let's just do it like this, right? So the left subtree looks like that. That's balanced, and the height is equal to 1. The right subtree is null. That's balanced, but a null tree has a height of -1. And now the difference in the heights is equal to 2. That's too big. So that's unbalanced. And the sense is, you know, this node could have gone over here. And then the tree would be shorter, and we'd still have the same information. So there's an example of an unbalanced tree. What about this one?
technically balanced, but I think it's unbalanced.
That is unbalanced. Why?
I would think because the nodes are not actually stretching correctly.
Mm-hmm.
Because you have to take those into consideration when you're doing the math.
Right. So if we were asking a computer to tell us whether this was balanced, it would go through these 3 checks. And this first check says the left subtree, which is this, has to be balanced. And that's not going to be balanced. And this third check is fine. This tree has a height of 3, this subtree, and this subtree has a height of 3. So the heights of these trees are close to each other. They're exactly the same. But the subtrees themselves are not balanced. And so the whole tree cannot be balanced.
So I think I can kind of see the algorithm we're going to use to check.
Mm-hmm.
So we're gonna check the left, check the right, and then we're gonna compare the two basically.
Yep.
And then kind of sort that out based on how many items we have, right?
Yep, you got it.
Okay.
So when we're checking to see if the left subtree is balanced, how do we do that? Well, we're going to ask our balance function, is this tree balanced? Well, it's going to take the left subtree and see if that's balanced. It's going to take the right subtree and see if that's balanced. And even if this were to come back balanced, right, this would have a height of 2, and this would have a height of -1, and this third test would fail. And so this will definitely not be balanced, and since that's not balanced, this whole thing's not balanced.
So we're going to do the log for each test for left and right, and then another test where we subtract the heights and check that, right?
Yeah, this will be a log n, and this will be just one calculation, but to find the heights will also be a log n operation. So the whole thing will basically be log n.
So we're not gonna use the height function to return the left and right height.
We are actually. So yeah, actually, I think this might be order n, not log n. It's log n to go from the top to the bottom, but we're going to have to do that a total of n times, basically, to get to each node. So this will end up being either n log n or n. I don't remember which, but still not too bad. So let's look at one more example. Right, so here's another tree that is going to be unbalanced. And if we apply these three rules, first we would check the left subtree, and that's definitely going to turn out to be balanced. And then we would check the right subtree, and after we go through all of the recursion, this will turn out to be balanced. Because, I mean, it's nice and full and fluffy, right? But then when we finally calculate the height for this third check, this left tree is going to have a height of 1, this right tree is going to have a height of 3, and the difference between those is too big. And so it's going to turn out to be an unbalanced tree. So we'll always have to do all 3 of these. But we don't have to do it. We're going to tell the computer to do it. Because we're programmers and we're lazy. So what does a balance function look like? So I'm going to write a function called isBalanced, and I'm going to say return 1 if balanced, 0 if not. And so first thing we're going to do is see if the argument is null. If t equals null, return 1. Tree's balanced. Otherwise, we could do basically one statement if we want. If is balanced, t arrow left, and is balanced, t arrow right, and absolute value of the height of t arrow left minus the height of t arrow right. This is pseudocode. is less than or equal to 1, return 1, otherwise return 0. And you can turn this into C code pretty easily, right? But this is an exact implementation of this description of what it means to be balanced. If the tree is null, it's balanced. So if t is null, return 1. If all three of these are true, so if the left subtree is balanced, and we're going to use our isBalanced function, right? And if the left subtree is balanced, this will return a 1, which is true in C, in which case we'll call isBalanced on the right subtree. And if that's balanced, it'll return a 1, which is true in C, in which case we'll go on and we'll calculate the height of the left and right subtrees, subtract them, calculate the absolute value, see if that's less than or equal to 1. If all three of those are true, we've satisfied these three criteria, we return 1, saying the tree's balanced. If any of these fail, if the right subtree is not balanced, for example, isBalanced will return 0, which is false. This if statement will fail. We won't return 1, so we'll return 0, saying it's not balanced. And so it's, again, a few lines of C code to write a function to test whether the tree is balanced. But there's a lot of work going on.
The handwriting of, is that a DOS or ABS?
Absolute value.
Oh, thank you.
Yeah, well, I just made it worse. But yeah, that's this step right here.
That's in the math repository or library.
Maybe, maybe not. You can just do this with an if statement. Or you can write your own absolute value function. I don't know if an integer absolute is built in or not, and if it is, I don't know what it's called, because I think APS works on doubles. ABS works on doubles. But I usually just make my own, my absolute function, and it's a one-line function. But, that's why I say this is pseudocode. Say again?
Return. It's just basically if it's less than 0, return, whatever your integer.
Yeah, so my absolute x, return x is less than 0, negative x colon x. So it's a one-liner. So if x is less than 0, this returns negative x, otherwise it just returns x. Or, you could do if this is less than 1 and bigger than minus 1, but you don't want to call the height function a bunch of times, so maybe, save this in a variable and then say if that variable's bigger than or equal to minus 1 and less than or equal to positive 1. So there's different ways.
Can I see that function one more time? Just so I get a general idea.
In my abs?
I've never seen that. Yeah, I've never seen that laid out like that.
So that's the ternary operator, or interrogation. So if this is true, then it evaluates the thing to the left of the colon.
Okay.
It's kind of like the equal if statement in Excel. All right, so that's balance, and that's how you can code the balance function for PA4, because you're required to have a function that takes a tree and tells you whether it's balanced, so that you can print the result in the top of the dump command. And so that's just a function called balanced. Takes the root of a tree, returns a 1 or a 0, and that uses a function height that takes the root of a tree and returns an integer, which is the height. All right, so let's do a break, and when we come back, let's talk about deleting from a tree. So we'll come back in about 4 minutes and start talking about node deletion. Yeah, you can get absolute value by multiplying by itself and then square rooting, I think. Or dividing by itself. Yeah, I think you got to take the square root. Because minus 1 times itself would be 1. Or hey, go into binary and take the 2's complement. Alright, let's talk about deleting from a tree, not form a tree. And here's a sample tree. And we want to delete from this. Now this is a binary search tree, so it has this property that, you know, at every point stuff to the left of a node is smaller, stuff to the right is bigger. And we want to preserve that property because that's the property we use when we search the tree, when we try to add something to the tree, and so on. And so, if we want to delete, you know, something like a 70, that's easy. Just, you know, get rid of it. If we want to delete the 30, just get rid of it. But if we want to delete something like the 60, we have a challenge because the 60 has 2 children. And when we delete this, its parent is going to have, you know, an open spot to adopt 1 child. But 60 had 2 children. And so if this adopts the 70, what happens to the 50? And, you know, the 70 itself might have some children over here. And if we were to, you know, replace this with the 50, well, the 50 might have some children over here, and it wouldn't be able to adopt 70 as its right child. And so there's this question of how to delete a node from the tree. And the worst case is when we delete the root. Because every node in the tree is a descendant of either the left child or the right child of the root. And if the root's gone and we don't do something to keep these 2 children attached to our tree, we lose not only those children, but we lose everything in the tree. And so we have to figure out, you know, what can we do to remove that 40 in this case, but still keep the rest of the stuff in the tree.
It seems like balancing would be a similar undertaking, because let's say you added another couple of numbers and the tree becomes unbalanced, something else might need to become the root.
Mm-hmm.
The entire tree, the middle of the whole tree, and then you need to resort, right?
Yeah. And the key to balancing a tree will be to keep it balanced as we add or delete to or from it. But we're going to have a similar challenge, exactly, because, you know, if the root is 10 and we're adding a 20, 30, 40, 50, 60, 70, eventually that root's got to change. Right, because we know that 40 probably has to end up close to the root, and so that will be a similar kind of algorithm. For deleting, it turns out that though most of the time this is pretty easy to do. So again, we use recursion, and we make the observation that, for example, if I want to remove the 60 from this tree, all I have to do is remove the 60 from this tree, and then whatever the resulting tree is, make that the right child of 40. And, you know, whatever I have to do to remove 60 from here, as long as that leaves me with a binary search tree, I take the root of that tree, make it the right child of 40. Everything over here is intact. Everything over here will still be bigger than 40. If this is still a BST, the whole thing is a BST. I'm done. So we're going to lean on recursion again, and we're going to say, here's how we delete some piece of data from a tree. And just like in adding, when we add a node, our add function returns a root. Our delete function is also going to return a root. So this would be something like, for example, a struct node star, or an uppercase node if you type def. So this is going to delete data from T and return the root of the new tree. And the first 2 cases are truly trivial. So if our data is less than the root node's data, what do? Delete from the left subtree. delete from T arrow left, comma, data. Do whatever you have to do to delete your data from this tree, and the delete function will return the root of that tree. And so let's just set T arrow left equal to what we got when we deleted. And we're supposed to return the root of the tree, so we'll just return T. That's the root. The root hasn't changed. So that's one possibility. A second possibility is if the data is bigger than the root node. And we do exactly the same thing on the right. We set T arrow right, the root node's right subtree, to be equal to the result of calling delete to remove our data from T arrow right, the right subtree. And then we return the root of the original tree. So there's 2/3 of our delete algorithm. What to do if the data sits to the left of the root, what to do if the data sits to the right of the root. What's missing from this is what to do if the data is equal to the root. What if we want to actually delete the 40? And this is where the hard work starts. So our delete function will begin with two recursive possibilities. We might recursively delete from the left or recursively delete from the right. And I'm assuming the data we want to delete is in the tree, so I'm not going to worry about the case where our tree is null. But if you don't know if the data is in there, you might have a case where, you know, the tree itself is null, in which case you just return or something.
I have a question real quick.
Sure.
It looks like this is our function. The struct node delete T data is our function, correct?
Mm-hmm, correct.
And we're calling within the function.
Yes, we are. That's the recursion magic.
What the heck?
Yeah. But this is the same thing we did with the height function, right? We said to find the height of a tree, we find the height of the left and right subtrees, add 1, and return that. Or to tell if
traversing the tree, basically, right? That's all it is.
pretty much, yeah.
It's just saying if the data is too big, go one way. If it's too small, go the other way.
Mm-hmm.
Until you've found that data, so it's just recursively calling it until
Right.
you tell it what to do.
Right. And when we wrote the isBalanced function, it makes calls. Thank you. It makes calls to the isBalanced function, right? That's our recursion again. We're calling this function inside itself. Well, same thing here. We're calling delete inside the delete function, and that's the whole kind of sketchy part of recursion that we're working towards understanding better through this assignment. But yeah, if that looks weird, that's good, because it is weird.
I just finally caught on that we've been like calling it from inside itself, and that
Mhm.
is
And
so foreign to me.
yeah, it is. And the cool thing is, at some point, we can stop worrying about it. At some point, we'll just kind of accept that this works. And we'll actually be able to think in terms of how can I break this problem into other versions of the problem. And we'll start, coming up with this stuff. And it will stop seeming weird for a while. And then it'll seem weird again. And it goes back and forth like that. Sometimes it weirds me out when I'm teaching it. I've been doing this for decades, and sometimes when I'm talking about it, part of my brain is still going like, what? and I mean, that's part of the fun of doing this stuff, because it is weird.
It's real good practice for like functional too, and sometimes like pure functional like this comes in handy for thread safety.
Mm-hmm. Yeah, when you get into functional programming, that's a similar can of worms that I don't have as much experience with, but I've always been intrigued by.
I've ran into some deadlocks in some other languages, and that's a real fun problem when you get into objects with threads.
Yeah, we'll do a little of that in 223, and then you'll do a lot of it at university, and deal with competing processes and resource contention and stuff like that. Just for a Freaky Friday moment, right? This, personally, to me, this is somehow related to the ego. This is like a sense of self. and we're creating code that in some sense is aware of itself to the degree that you can say we are aware of ourselves, even if we're just kind of thinking about, oh, I'm thinking that I'm thinking about something, right? But we have that ability to self-reference, and I think for humans that's tied into the I, right? Uppercase I, the ego, the sense of self, and all the stuff that comes with that, with like seeing the world as dualistic and so on and so forth. So there's some edgy stuff going on in here, which is part of why I think it feels, kind of freaky, kind of magical, kind of annoying, kind of delightful, all of that stuff. But yeah,
the thing that always gets me here is like, even with this one is even a little weirder than some of the ones I wrote, because they usually start out with like, if root is null in some form or another, return something and get out of that function before you do anything else. But there's no like stopper here at the bottom. Well, there is a stopper here at the bottom once you can't traverse any further into the recursion. But it just isn't immediately obvious to me where it stops,
Right. It will stop when neither of these conditions are true, because the remainder of this algorithm is not recursive. It's going to be an iteration. And so if we're trying to delete a 20, this will say, let's delete 20 from this subtree. And when we call delete with this tree and a value of 20, both of these ifs will fail. 20 is not smaller than the root, and 20 is not bigger than the root. So we're going to go on to the next page. And that's going to be the harder part of it, is how do we delete the actual root. And we'll just return from the end of that algorithm, and then we're done deleting from the left. This will set the left node to that, and our original delete call will return. But yeah, it is a different flavor of recursion. So let's...
I have a question.
Yeah.
You said in one point recursive functions were basically adding one to something, but here you're saying that recursion is calling a function within itself. Is it the same thing?
Yeah, so when you have a recursive height function, let me see if I still have that, where we say return 1 plus the maximum height, that's the sense in which recursion is kind of adding 1, right? We're calling the height here, we're calling the height here, and then we add 1 to one of those values we got back and return it. And so at some sense, each time that we call ourselves, when we come back from it, we've added 1 to a return value. And when we return to whoever called us, we're going to add 1 to the value we got back. And so if you call something, 6 times, when you come back, you're going to end up returning 6 plus whatever that lowest level call returned, which would have been -1. And so if you have 6 nodes, your height function will return a 5, which is the right value. But that's sort of just in this case, but it pops up in a lot of cases. But in the case of deleting, it's not so much adding 1 as it is really just kind of moving to the right spot. All of this is just getting down to where the number you're trying to delete is the root of some tree. And then we're going to do a separate algorithm to delete that root. And then when we return, we're just going to pop back up through the stack.
If we were assigning it to an integer or something like that, then we could return that value and whatnot. But in this case, we don't really care, right?
Mm-hmm. Right.
Yeah.
All right, let me hop on Canvas a second. Canvas always logs me out. Doesn't matter how recently I was logged in, and I say stay signed in, but I always get logged out, which is good.
It's funny, I've been on Canvas all day one time and never got logged out.
That's nice. I mean, it's good because I never forget my password this way because I have to type it in every day.
At least you're seeing the positives, right?
Yeah, right. All right, so let's look at how we delete the root of a tree.
And now, are we going to assume there's a root, we're not going to assume. I mean, if the tree is null.
If the tree is null, we can just return.
Okay.
And you would want to do that before you do these checks.
Yeah.
So if you're going safety dance, right, you can say if t equals null, return null.
Just return. Okay.
But that would imply that we were trying to delete something that wasn't in the tree, and I'm not sure that would do the right thing anyway.
That's going to be not even a possibility, basically, right? Unless for some reason our database doesn't.
Yeah, if we tried to delete 75, right, we'd get down here, we'd try to delete 75 from a null tree, it would return null, put a null on there, and it would just return, it wouldn't do anything. But yeah, for us, that's not going to be a case, because when you say delete in your main program, you're going to call search first and see if the plate's in the tree. And if it is, then you can call delete. If it's not, you can just say plate's not found.
Gotcha. Okay.
All right, so let's delete the root of a tree. So there's multiple ways you can do this, but I'm going to be really specific on what algorithm we use. And I'm going to put a note in the lecture video saying you must use this algorithm. So here's our tree, and it's got some stuff in it. And there's some stuff over here, and so on. And we want to delete the root. Okay, here's the algorithm we're going to basically use. Basically, we're going to replace the root with the largest node from the left subtree. So to delete this root of the tree, we're going to find the largest node in this left subtree, and we're going to move that to be the root of the tree. So first of all, why is that a legitimate thing to do? Remember, we need to make sure that this thing is still a binary search tree. We need to make sure that at each point, everything to the left of a node is smaller, everything to the right is larger. If we put the largest node from this left subtree, right, so here's the left subtree. If we take the largest node from here and move it to the root, we still know that everything in here is smaller than the root, because the root is the biggest thing in this whole subtree. So if we put this up here, everything here will still be smaller than the root. And within this tree, it'll still be a BST because we're not going to change everything. And over here on the right, everything in here will still be bigger than the root because we're not going to touch the right subtree. So we'll still preserve the binary search tree order. The one thing...
Question, we're turning a leaf into a root?
This is not actually a leaf. In this tree, this would be the largest thing in the tree.
Yeah.
It could be a leaf though, and yeah, whatever it is, we're going to take that and basically have its left child be here and have its right child be here. So this will become the root of the tree. And there's one major complication when we do that, which is if we change this thing's left child to be this node right here, what happens to all of these left children that this node had? They're going to be orphaned if we don't pick them up somewhere. But it turns out the largest node in the tree is going to be the rightmost node. And if we take its parent is now going to be free to adopt on the right this subtree that's being orphaned. So I'm going to put a node in here, largest node's parent can adopt largest node's child. And child is singular. This node cannot have a right child because if it did, guess what? That right child would be larger and this would not be the largest node. So if this is the largest node, it has nothing to the right. So it has at most one child to the left. When we move this, its parent is going to have an open spot on its right. It's going to adopt this node's left child. So we're getting into some complications now. So let's draw a picture, and let's do what I've been describing is helpful when you're working with large data structures in memory. Let's use temporary labels. So here's our tree. There's stuff on the right that I'm not worried about. And there could be other stuff here. All right, so all of this stuff, this is the left subtree. This is the main thing we're going to be examining. And in here, we're going to have a node which I'm going to call largest. That's the largest node in this subtree. And we can find the largest node by basically starting at the root of this subtree and just moving to the right. Keep moving to the right, further and further, until there is nothing more to the right. That's the largest node. You could prove that using mathematical induction, by the way, but we won't. But everything else above it, or everything to the left, is going to be smaller. So this is the largest node. I'm also going to label that node's parent. I'm going to call it parent underscore largest. So my delete algorithm is going to be the following. 1, find largest and parent of largest. Step 2, I'm going to have this node's parent adopt the largest node's left child. And that's just going to be something like parent of largest, arrow right, equals largest, arrow left. All right, that's going to do this. So we're not going to orphan the largest node's left child. Then we're going to move largest to be the root. So how do we do that? We're going to say largest, arrow left, equals the root node, which I'm calling t, arrow left. And largest, arrow right, equals t, arrow right. All right, that's going to take this node, and its left child is now going to be right here. Its right child is going to be right there. That effectively makes this the root of the tree. We're not moving it in memory, but we're basically saying if I go to the left of here, I'm going to end up right here. If I go to the right, I'm going to end up right here. And then the last thing is we can free that old root node t. And then we have to return the root of the new tree, and that's just the node largest. So that's the new root. Hey. So 5 steps. And this is the ideal case. There's going to be some special cases we need to deal with even amongst these. All right, so moving to the left subtree, find the largest node, find its parent, and then make these adjustments to what's pointing to what. Have the parent point to the largest node's left child on its right. Have the largest point to the roots left and right on its left and right. Free the root from memory, and then return largest as the new root. All right, so questions so far, because we're going to make this more complex.
For the temporary to find the parent, would you just say basically while this one points, basically make 2 pointers saying like while largest left pointer to left or whatever, something like that, is not equal to null, so that you're like back a step. I haven't really worked out the whole statement, but
That's basically right.
okay.
So how do we find the largest and the parent largest? So we'll do something like, temp let me call it previous. All right. So previous equals TO over left. So previous is going to be this node right here. I'll take the hit. I'll call it parent largest. I should have used shorter names. Okay, so I'll start off with parent largest equal to T arrow left. And largest equals parent largest right. So seed your algorithm. So this is largest, this is parent largest, and then do some kind of loop while largest right is not null. Move along down the list. So set largest equal to largest right, set parent largest equal to parent largest right. So we start off with parent and largest. Largest has something to the right, so move down. Parent and largest. Largest has something to the right, move down. Parent largest. Largest still has something to the right, move down. Parent largest. Now largest right is null, so we stop. And at that point, parent is the parent of the largest node, and largest is the largest node. But there's a special case to worry about in here, which is what if this node doesn't exist? So special case. What if there's nothing to the right of the root of the left subtree? In other words, what if the root of the left subtree is the largest node in the entire left subtree? In that case, we can't, do this because we don't have a parent of the largest on the left to adopt the subtree of this, and so on and so forth. But in this case, moving this 10 to the root is really simple. Whatever's on the right here, just make that the right of this node, free the root. So there's this extra special case, which is if the left subtree has a root with nothing to the right, in other words, if the root of the left subtree is the largest thing in the left subtree, then we basically just change that root to pick up the original root's right child on its right. So you want to do a lot of drawings on paper and work through these cases and see what should be happening before you try to write the code to make that happen. If you know exactly what you want to have happen, writing the code will not be that challenging. The bigger challenge is just deciding what you want your algorithm to do, not how to write the code to make it happen, because that's going to sort of write itself. It's really understanding, what are the different cases. And one case is, the left subtree has nothing on the right, in which case this should be the new root of the tree, and so I'll just pick up this node on its right, free the root, return this. A second case is there's at least one child to the right, so now march through until you get to the largest node, remember what its parent is along the way, and then do these kinds of things. Have the parent adopt the largest left child, move this to the root, free the original root, and return this as the new root. So that's another edge case. And there's one other edge case. Which is I want to delete the root of this tree, and there's nothing to the left. The entire left subtree is null. Well, in this case, and this case only, I have to do something different. I cannot replace the root with the largest node from the left because there are no nodes to the left. So in this one case, you get to do something different. which is just change the root to whatever's on the right of the original root, free this from memory, return this. In other words, just move the root down one spot to the right. Alright, so we've got a big long algorithm now, right? Delete is huge. And you definitely don't want to start delete until the rest of your code is working. Because you want to know you can add to a tree. You want to know you can look at a tree using your different traversals. You want to be able to make a small database file and ingest that. And you want to know that your commands for like dumping and so on will work. And you want all those pieces in place before you try to link in the delete function. And delete is just one function. Delete, and to call it from your main program is just going to be something like root equals delete root, comma, whatever you parsed your integer into, your number. And I would do this with integers, right? I'd copy your code and write it for integers, or develop PA4 for integers and switch it to strings at the end. So that you don't have to worry about string compares and string copies and all that. Your choice. So the delete function itself, right? It's got some recursive stuff in the beginning. See if we should delete from the left or right subtree. And then it's got a long section for deleting the root of a tree. And that involves finding the largest node in the left subtree, which could be an edge case. If there is no left subtree, we're just going to move the root to root arrow right. If there is a left subtree, it's possible that that left subtree does not have anything to its right, in which case, you know, our left subtree looks just like this. It's got a root node and nothing to the right. And in that case, we make the right node of this the right node of the original root. Or it could be there's at least one node to the right of the left subtree's root, in which case you march down, find the largest, remember its parent, and then do this kind of stuff. So lots of edge cases. Alright, this is where I make a sales pitch for commenting your code. Unless you get really lucky and you write this code the first time and it works perfectly, you're probably going to have to do some debugging. And debugging code like this, right, means sitting inside GDB, stepping through your code, trying to understand what's happening. And you're going to have, you know, a bunch of statements of C written like this, and like this, and so on. And how do you debug that? How do you figure out what's going on in here, and so on? So here's a trick to debugging this kind of code, right? In GDB, you can single step through your code. It'll show you a statement that you wrote. You can say next, and it will execute that statement. And then you can look at values in memory. You can look at things that are pointing and see what they're pointing to and so on. But if I say something like largest arrow left equals T arrow left, and I execute that statement, and then I look at largest left and I look at T arrow left and I see that they're the same, all I'm doing really is saying, hey, the universe still works. Right? The CPU did exactly what I told it to. Well, we kind of believe that's going to happen anyway. What you really, really need when you're debugging is a comment here which says, you know, adopt largest node's left child on tree's left side. And now you execute this statement and you look at the memory and you draw a picture of what's happening in memory and you say, did I adopt the largest node's left child on the tree's left side? You've got to know what the intent of your statements are. And that's what your comments tell you. If you get to this point in your program and you execute the instructions and you look at your data and you see that this did get assigned to that, that doesn't help you know if your program's doing the right thing. It lets you know if the CPU is doing the right thing. But is this statement reasonable to have here? Is this an operation I wanted to perform? Well, to answer that, you need to know what the purpose of this operation was. That's what your comments say. They don't say copy T left to largest left. They say take the original tree's left child and adopt that to the left of the largest node. And so you got to have good commenting in your code while you're developing it, so that as you're going through the debugger and you're looking at each statement and seeing what it did in your memory, you can look at your code in the comments and say, does this make sense? Was this the right thing to happen? If you look at a node and it's suddenly null, should that node be null? I don't know. I mean, the statement said make this null. It made it null. Cool, the CPU works. Was there a good reason for this to happen right here? Where am I in this set of, 15 steps for deleting a node? Was this an appropriate thing to happen, or did I miss closing an if statement somewhere?
Would you be able to go back to the variable real quick? Just as far as the parent and stuff, I'm just kind of looking at the picture and.
So which variable?
To find the parent and the largest.
So we sketched out a little bit of code here.
Yeah, that one there.
Right, so start with the left of the root, and the largest node starts off as the right child of that root.
Hey Andrew, can you mute yourself? Thanks, bud.
Right. So start off with parent of the largest right here, largest node here, and then keep moving in tandem until you get to a spot where the largest has nothing to the right.
Okay, I think I was looking at it for some reason as root right is the parent largest, and I was like, well, that's kind of
Yeah,
weird.
all of this begins at the root of the left subtree.
Gotcha, okay.
And then it's basically what we do in our linked list where we have previous and current.
Yeah.
But there's a special case if there's nothing to the right here, right? This would segfault if there's nothing to the right there. So this would be null, and you'd need to notice that.
That's basically if this is null, then just.
If it's null, then it's a special case. We can't do this, right?
Yeah.
If the largest is null when we set this up, then what we want to do is basically take this, what we're calling parent largest, and have it adopt root arrow right, and then return this as the new root of the tree.
Gotcha.
And unfortunately, a lot of these special cases are guaranteed to come up, right? When you're deleting a node, you're going to recurse until you get pretty far down in the tree sometimes, and you're going to come up with all of these cases. It's hard to do a test case where you won't. You can do it, but again, you got to draw lots of pictures. You've got to go through this algorithm on paper and then ask your code to reproduce it. All right. So I have office hours tomorrow. I have office hours Tuesday, and we have class again Tuesday. This should be enough to at least start thinking about deletion, but like I say, you probably want to code it at the very end. So if you're working, over the next few days on PA4, you probably won't get to the delete part yet. When you're ready to develop this, you could do it with a tree package of integers, right? That's less complex than dealing with the strings and the plates and the mallocs and all of that stuff. And build it up in pieces, right? Just make a main program that builds a tree, use your add function, and then, maybe make a tree like this. And try to delete the root. And in this case, you're going to go directly into the delete the root. You're not going to recurse. And you're going to come here, and this is going to be parent largest and largest. You'll come down once, this will be largest, this will be parent largest, and you'll do these things. And if that does not work, right, it's a pretty small test case to experiment with. And, a few times you'd have to step through the loops in the debugger. And so that would be one way to start. But again, you're doing this on paper before you code it.
And as far as the balance goes, I noticed the test case, or the test sample code says no. So we should assume ours won't be balanced as well.
Yes, but you're welcome to try it with other database files that would end up with a balanced tree, and I'll definitely do that. I'll have some smaller files, and an easy one would be bat, ant, cat. If I feed in those 3 license plates, that will end up being balanced, because that'll make a nice tree like this.
Gotcha. Okay. So that's a good way to evaluate whether or not the function's actually working or not.
Yeah, yeah.
Okay.
All right, I will leave you with one Freaky Friday thing. So there's a link under resources now on Canvas called Coding Haikus. This is a book I put together last year during 222 and 223. This is a book of haikus that are related to all the things that we're talking about in 224, 222, 223. And it's meant to be fun and lighthearted, but there's haiku versions of a lot of the things that I'm saying, including things about recursion and tricks for debugging and so on and so forth. So if you need a break from coding, right, or you're looking for different ways to think about some of the stuff we're talking about, feel free to download this and browse it at your leisure. And it's a different kind of additional text for the course. So I'll leave you with that for weekend entertainment if you like. All right, I've got to scoot off. Like I said, I have an appointment in 20 minutes. So I'm going to call it quits here, but we'll talk more about deletion on Tuesday, and we'll also start talking about other things we can do with trees as far as different ways to traverse trees. We'll deal with whatever questions have come up, and then we're going to start talking about dynamic programming, which will be our next major topic and will be the subject of our final programming assignment. All right, so I hope everybody has a great weekend. If I don't see you tomorrow, have a good one, and I will see everybody next week. Was there a last question? Okay, cool. All right, thanks, you too. Thanks, take care.